இந்த வீடியோவில் ஒன் டைமென்ஷன் ஹீட் ஈக்குவேஷனை டிரைவ் பண்ணுவோம். பேசிக்காக டெரிவேஷன் ஆஃப் ஒன் டைமென்ஷன் ஈக்குவேஷன் பற்றி பார்ப்போம். ஓகேவா? ஸோ பேசிக்கலி டெரிவேஷன் ஆஃப் ஒன் டைமென்ஷன் ஹீட் ஈக்குவேஷன். ஓகேவா? ஹீட் ஈக்குவேஷன். ஸோ நம்ம என்ன பண்ண போகிறோம், இது ஒன் டைமென்ஷன். ஓகே, ஸோ அதுக்கு முன்னாடி ஹீட் ஃபினாமினா பற்றி இம்பார்ட்டண்ட் பாயிண்ட்ஸ் நம்ம தெரிஞ்சுக்கலாம். ஓகே, டெரிவேஷன் ஆஃப் ஒன் டைமென்ஷன் ஹீட் ஈக்குவேஷன் பண்ணுறதுக்கு முன்னாடி ஸோ இம்பார்ட்டண்ட் ஃபினாமினா ஹீட் ஃபினாமினாஸ் பற்றி பார்ப்போம். ஹீட் வந்து எப்பயுமே ஃப்ளோ ஃப்ரம் ஹை டெம்பரேச்சர் டு லோ டெம்பரேச்சர். ஹீட் ஃப்ளோஸ் ஃப்ரம் ஹை temperature to the low temperature. ஸோ இது ஒரு ஹீட் ஃபினாமினா. இது எல்லாருக்கும் தெரிஞ்ச விஷயந்தான். நேச்சுரலாக இப்படி தான் நடக்கும், அன்லெஸ் அதர்வைஸ் யூ ஃபோர்ஸ் டு டூ இன் ரிவர்ஸ் வே. ஓகேவா? ஸோ செகண்ட் பாயிண்ட் என்ன அப்படின்னு பார்த்தீங்கன்னா, the rate of heat flow across an area is proportional to the area of cross section and temperature gradient. ஸோ ஏதோ ஒரு மெட்டீரியலில் ஒன் டைமென்ஷன் டூ டைமென்ஷன் மெட்டீரியலில் போகுதுன்னா அதோட கிராஸ் செக்ஷனல் ஏரியாவுக்கு ஹீட் ஃப்ளோ எப்படி இருக்கும்னா கிராஸ் செக்ஷனல் ஏரியாவுக்கு ப்ரப்போர்ஷ்னலாக இருக்கும் அண்ட் டெம்பரேச்சர் கிரேடியண்ட்டுக்கும் ப்ரப்போர்ஷ்னலாக இருக்கும் அப்படிங்கிறது. ஸோ பேசிக்கல்லி செகண்ட் பாயிண்ட் இஸ் த ரேட் ஆஃப் ஹீட் ஃப்ளோ, ஹீட் ஃப்ளோ across an area is proportional to எது? ஒன்று cross sectional area, ஓகே. செகண்ட் வந்து temperature gradient. These are the two important points. ஓகேவா? ஸோ தேர்ட் பாயிண்ட் என்ன அப்படின்னு பார்த்தீங்கன்னா, ஓகே, தேர்ட் பாயிண்ட் வந்து the quantity of heat in a body is proportional to its mass and temperature. ஓகேவா? The quantity of, basically third point is quantity of heat in a body is proportional to what? Proportional to its mass. First point is mass, second is temperature. ஓகே, ஸோ ஒரு பாடியில் இருக்கிற ஹீட்டோட குவான்டிட்டி எதை பொறுத்து இருக்கும்னா அதோட மாஸ் அண்டு டெம்பரேச்சரை பொறுத்து இருக்கும். ஓகேவா? ஸோ இதெல்லாம் தான் வந்து ஹீட் பற்றி நம்ம தெரிஞ்சிக்க வேண்டிய இம்பார்ட்டண்ட் பாயிண்ட்ஸ் ஆர் தி ரிலேஷன்ஸ். ஸோ அடுத்தது என்ன பண்ண போகிறோம் அப்படின்னு பார்த்தீங்கன்னா, நம்ம வந்து ஹீட் ஈக்குவேஷனை டிரைவ் பண்ணுறதுக்கு ட்ரை பண்ணுவோம். ஓகே, ஸோ வில் ட்ரை டு டிரைவ் தி ஹீட் ஈக்குவேஷன். ஓகே, ஈக்குவேஷன்ஸ் டிரைவ் பண்ணுறதுக்கு ஃபர்ஸ்ட் என்ன எழுதுவோம் அப்படின்னு பார்த்தீங்கன்னா, we will draw some figure. Let us draw some figure, something like a rod. Take some rod, right? We have some rod, and here what we have is some points in the rod, 2 points in the rod. Let us say this point, this is a point P, this is point Q, and this is the point at O. This point P point is x distance from the origin, and basically since it is a one dimension we will call only the x-axis, and this rod is now lying in the x-axis or along the x-axis. So the distance between these 2 points we will be calling as delta x or dx or something like that. Okay, delta x. So therefore this distance is x and this distance is dx. So therefore the q point is basically at the distance of x plus delta x. Okay, this q point is at the distance of x plus delta x, because this distance is I'll put it in different color. Basically this is the shaded regions, this is the small dx segment we are considering, dx segment from the rods. And in this what happens, right? So the heat is flowing, and the flow rate of, or the heat is decided by the, or the heat quantity or the temperature or heat is decided by the position and the time, right? At any particular instant of time, the heat or the temperature depends on the position and the time. Therefore this is how I will be writing the expression. And what we do now is try to solve this. Okay, so this is the equations, that description for our phenomena. So heat flows from high temperature to and so on, that we have looked at. And now what we will do, we will try to write the amount of heat contained in the element is, which element? PQ element, right? The amount of heat contained in this, so this element is, so this is a small elemental region. So how much that? Okay, so the first amount of heat contained in the element, okay, contained in the element P comma Q is proportional to its mass and temperature, is proportional to, is, right, is proportional to, right, proportional to its what? Its mass and temperature, mass and temperature. So therefore what I will do, so I will write the heat equation, or heat H of T is proportional to mass times U of x comma t. Okay, U of x comma t. So this is how I'll write the heat relation now, right? So heat, how much heat will be at a given instant of time t, so that will be proportional to mass into temperature, that is U of x comma t. The temperature is now basically the function of two quantity or two variables, position and the time, right? Position and the time. So then what we will do, we will try to modify this equation in terms of the dimension. So for that what I will do, I will take the density relation, right? I take the density. We have taken some rod, right? So we have taken some rod, that which is basically the one-dimensional rod. So therefore we will be having only the length, right? We will be having only the length. So therefore what happens here, mass density is equal to mass by length, because the basically the one dimension. So therefore I just put a length instead of if it is a two dimension, we will be putting the area, three dimension volume. So since it is a one dimension, we will put the length, and we want to convert, basically we want the mass from this. So therefore what I will do, mass is equal to rho times the L. So this mass value or the relation I will substitute in the heat relation, that is H is directly proportional to M into U, right? So therefore what I will get, so M times S into, right, what I will do now, so this is the equation. So now what I will do, I'll slightly modify this equation, H equations. Otherwise, before going to this, we can also do the following. What we can do is we can remove this proportionality constant. H is directly proportional to, right? So therefore after removing the proportionality constant, I will be getting some term that is actually the S, specific heat capacity of the material, and then what we will have is M times U of x comma t, x comma t. So therefore what happens now, so this is the heat equation, and we know S is specific heat capacity, specific heat capacity of material. So whatever the material you have taken, so that material specific heat capacity is S. So that comes when you basically remove the proportionality constant. Basically when you remove the proportionality, the constant that you guessed is basically the specific heat capacity of the material. So that is what we have now in the H relation. And now we will try to find out the mass, replace the mass with the in terms of density and the dimension of the material. So therefore what we will do, so rho is equal to, right, density of material generally mass by volume. So since it is a one dimension, what I will do, I will just put length because it's a one dimension. So from this what I will get, so mass is equal to rho times L, that is actually the density times the length of the material. And so you can put this value in the heat equation, that is H, right? S basically rho into L, and Ux, right, Ux, right? And if you basically here what I will do, so H of T is equal to S into M, right? So basically M, in place of M I will put rho times, in place of L I will put del X because that is a small dimension, therefore del X I will put into U of right, U of x comma t. So this is what my H values now, is the relation that I have it now, right? So then what I will do here, the rate of, right, right, the rate of heat flow, right, the rate of increase of heat, right, basically H, right, rate of increase of heat இல்லையா, so heat in the material, right, in the material or element, in the element PQ is how much. So basically I have to differentiate this H value. So therefore what happens, so H dH by dt is equal to, right, so dH by rate of change of the heat with respect to the time, right, with respect to the time, which is equal to how much, right, which is equal to how much. So S times, right, S times rho, density of the material, times del X times du is there, right, du becomes basically u is there, so that becomes dou, what happens, so dou u by dou t. Basically it's with respect to position, right, with respect to time with respect to time it is changing. So therefore that u becomes, if you look at here, this is u of x comma t, that becomes du by dt, right, so that becomes du by, so dt we will be getting. So now this is actually now what is it, so here dH by dt is basically rate of increase of heat in the element pq, right? So that's what we got it. So I'll take I'll put a drawing box here. So then what we will do, u depends on two variables and so on, that we know, because it is with respect to heat, will be temperature will change with respect to the position from the point of the starting point to the end point, and also the time, what time and so on, right? So therefore what happens now, I'll take the help of Fourier's law of heat conduction states that, right? I'll take the Fourier's law of heat, what it states, Fourier's law of heat conduction states that, right? Fourier's law of heat conduction, heat conduction states that what it states, that the rate of flow of heat at a point, right, at a point x of the beam is proportional to the negative of the temperature, gradient, negative of the temperature gradient. So therefore what happens, so this is the statement, so therefore with respect to this statement, or with the help of this statement, I will try to find out the net heat flow at 2 points, one at the point P. So the net heat flow at point P, right? So now I will be trying to find out the heat flow at point P and point Q. So for that I will be writing the equations. Right? So how will I write that? For this, generally, how will I write this Fourier's law statement? So I can express this in the following manner: Fourier's law in the equation form or relation. So basically the rate of heat flow at any point is directly proportional to, right, dou u by dou x, right? Dou u by dou x. So this is the statement that we can have it. And so if I remove the proportionality, what I will get is the following. So that is actually, if I remove the proportionality, so the proportionality will give me the constant. That constant is actually called the what is called the thermal conductivity constant. If I remove the proportionality, I will be getting some constant. That constant is called as the thermal conductivity constant, that is dou u by dou x is there. So if I remove the proportionality, so the rate of heat flow is equal to some constant times, basically negative, right? Negative they said, and gradient of the temperature, that is dou u by dou x, right? Here the K is basically the thermal conductivity. K is thermal, right? K is thermal conductivity. K is thermal. I will write it little bit better. K is actually, what is this? Is actually K is thermal conductivity, right? So thermal conductivity is the K. So then what I will do is, I will just write the heat flow at point Q and heat flow at point P. These 2 points I will write the heat flow equations. So therefore what I will do, heat flow at point at P, heat flow rate is what? So R1, I will consider the heat flow at point P is R1, and that is equal to K times dou U by dou X into X. Okay, because at the distance from the origin, the point P is at X distance from the origin, right? Point P is at X distance from the origin, therefore dou U by dou X I will be writing it. So and the at Q, right, the heat flow, the right heat flow rate is heat flow rate is how much? The heat flow rate is how much? So Q, I will write it as R2, so that is actually minus K times, right, K times dou U by dou X into X plus del X, because the point Q is additionally shifted to del X point away from the X point, therefore or P point, so therefore X plus del X. So that is how we got the heat flow. So therefore net heat flow into the small element, right, the net heat flow across, right, the net heat flow, the heat flow across P, Q ரெண்டு இந்த ஸ்மால் எலமெண்ட்டுக்குள்ள எவ்வளோ நெட் ஹீட் ஃப்ளோ நடக்கும் அப்படின்னு பார்த்தீங்கன்னா, ஸோ தட் இஸ் ஆக்சுவலி டிஃப்ரென்ஸ் பிட்வீன் R1 and R2, R1 minus R2, because R1 the temperature is higher, will flow from higher to lower, so therefore we just simply write it as R1 minus R2. So therefore that will be K times, right, dou U by dou X into X. So this minus, and the already we have one minus, therefore plus K times dou U by dou X into X plus del X, X plus del X, we have this relation. So therefore now if you simplify or rearrange this, R1 minus R2 is basically K times, right, K times what you have is K times how much it is, dou U by dou X at X plus del X minus dou U by dou X at X. So this is how we will be getting the relation, and this is what your basically the net flow of the heat change, that is basically net flow of heat across PQ. So then what we will do is, according to the law of balance of energy, right, according to the law of balance of energy, what we will do, the rate of increase of heat in the element, right, the rate of increase of heat in the element P, Q is equal to how much? Net heat flow into Q, net heat flow into P and P, basically PQ, okay, PQ. So that is dou H by so that is actually what is that? So the rate of increase of heat flow in the element PQ is how much? So basically that is dH by, right, so that is dH by dt is equal to R1 minus R2. So therefore we have to equate these two terms, that is actually we have s times rho times delta x times dou u by dou t is equal to, right, k times, basically this is a k times basically dou u by dou x at x plus del x minus dou u by dou x at x. So this is what we will be having now. So therefore we can simply equated these two terms, because what is the increase of heat in the PQ element? So that is basically equal to how much of heat that has flown into the PQ element region, right? So that small elemental region, what is the heat that increased, right? What is the heat that increased? So that basically depends upon how much the rays in this region, right? So basically so in this region, how much increase has happened, how much T increase depends upon how much it flown into the this region, right? So therefore we will be equating these two terms and then doing the calculations. And what we will do now, so therefore we can simply modify this and get the relation, final relation. So basically we want the dou u by dou t, and so therefore what we will do, we can simply write dou, right, dou u by dou t is equal to, so all other terms you take it to the right hand side and then simplify it, right, simplify it. So k divided by s into rho, right, s into rho, and dou u by dou x at x plus del x minus dou u by dou x at x. Okay, so this is what we have it, and this is divided by del x. Okay, this is divided by del x, and what we can do now, so in the del x la vandu we can simply what we can do, now we can apply the limits, right, k by s dot rho. So that's what we have it, and so simply apply limits as del x tends to 0. So in the above, in the equation என்ன ஆகும்னு பார்த்தீங்கன்னா del x equal to 0 apply பண்ணிங்கன்னா, so what என்ன ஆகும்னா dou u by dou t is equal to, right, dou u by dou t is equal to, so என்ன modify ஆகும், எப்படி modify ஆகும்னு பார்த்தீங்கன்னா, right, so என்ன ஆகும், so k by, right, k by s into rho. Okay, அடுத்தது limit s del x tends to 0, and இது ஈக்குவேஷனை மேலே எழுதிக்கலாம், dou u by dou x x plus d del x minus dou u by dou x at x, so and divided by del x. Okay, so this is what we can, when as the limit x tends to 0 ன்னு இருக்கும்போது என்ன ஆகுதுன்னு பார்த்தீங்கன்னா dou u by dou t is equal to k by s into rho into limit of del x is equal to tends to 0 dou u by dou x, இந்த மாதிரி ஒரு ரிலேஷன் நம்மளுக்கு கிடைக்குது. ஓகேவா? ஸோ இந்த ரிலேஷனை எடுத்து நம்ம என்ன பண்ண போகிறோம்னா இப்போது, ஸோ வில் டேக் தி ஹெல்ப் ஆஃப் so using first principle definition of first principle, okay, first principle, So now we will use we will use the right using the first principle definition of differentiation what you will do. So for using the first principle definition of differentiation, so we know the relation limit. Okay, suppose if you have something like limit, right, limit delta x tends to infinity, right? So f of x plus del x comma t minus f of x divided by del x. If I have some relation like this, I can simply write it as dou f by dou x. So this is what the first, right, first principle definition of differentiation. So now we will use this expression, right, or we will take help of this expression and write our expression, this expression, right. So what we will do, using the first principle definition of the differentials, we can modify this relation in the following manner. So here if you look at, this is only the function, but in our relation we have the function differentials, right? The function is in differential, first order partial differential, right? This is in first order partial differential. So when it is only function, you have the first order terms, first order partial differential terms, and then the function. Since it is already having one differential, partial differential, so the order now will be second order. So that means instead of dou f by dou x, it will be dou square f by dou x square, because this partial differential also will be included, right? So then using this relation, our this final relation will be modified in the following manner. How it will be modified? So it will modify like dou u by dou t is equal to k thermal conductivity divided by specific heat capacity and density of material times dou square u by, right, dou square u by dou t square, right, dou x square, right, dou x square. So dou x square, because it is in x, right, this is in x, basically this is in x, and therefore dou square u by dou x square. Okay, so therefore what we can do now is we can simply simplify this further in the following way. Dou square um, u by dou x square is equal to what? So now I will simply call this as c square. Okay, so therefore our equation now dou u by dou t is equal to, so this term I will be calling as c square, so dou square u by dou x square. So this is our one dimension the thermal heat equations. So if it is a third dimension, this term x will be uh, uh, modified to r square, because x term is only for one dimension, If you are having a two dimension, it will have a xy or yz or zax. If it is a third dimension, it will be xy and z, or you can simply write it as dr square. So this is how we have to derive this equation. So now after this we will also see how to solve the problem based on this the one dimension thermal heat equations.